across the 7 seas, under the protection of armed escort, men and weapons of the United Nations move out to far-flung battlefronts, carrying the fight to the strongholds of the enemy. And the ships get through, busy docks near the scene of action. And case after case of American fighting planes, hard-hitting P-47 Thunderbolts. The job now is to hurl these Thunderbolts into action without delay. That requires the quick uncrating and assembly of the airplane under any conditions, anywhere. To make this possible, a simple, practical method of uncrating and assembly has been devised, by which the P-47, although it weighs nearly 7 tons, can be ready for battle without the aid of spatial equipment, such as heavy jacks, cranes, or hoists. To assemble a P-47 under field conditions, the only equipment needed is a standard set of mechanics tools, manpower, and the shipping cases themselves.
The first step in the whole procedure is for the crew chief to read the instructions that are fastened to the front end of either of the shipping cases. Important: do not remove shipping cases from trucks until after you have read these instructions. The instructions are simple but important. Each step must be carefully followed. The instruction book should be read completely so that the crew chief may have an overall picture of the job to be done. Then he can go to work. First, the truck bearing the wing case is drawn up behind the fuselage case. This provides an elevated surface on which the men can stand while removing the fuselage case top. The fuselage case must remain on the truck. The top of the fuselage case is removed in one piece. Take out the lag screws and pry up one end with a crowbar. This end is held up with a short piece of timber wedged into place. Two or three lag screws, which are inserted in each corner of the top, serve as towing posts, around which is looped a length of 1-inch rope. Now, with manpower, the top is dragged off the case onto the ground. After the lag screws have been removed from one of the sides, this panel can simply fall to the ground. And the other side is removed in the same way. Then, the ends of the case are taken off. We're going to need those stringers all through the job. They are pried loose from the sides of the case. They are sawed through the middle, and the two halves are nailed firmly together. Now we are ready to unload the wing case and remove its contents. For this job, you need a pair of skids and the 1-inch rope. Hey, go easy. That case weighs over 3 tons. When its top has been pulled off, the sides and ends of the wing case are removed by the same methods used on the fuselage case. After the hinge fittings in the wing case have been loosened, approximately 50 men, using the fuselage side stringer sections for lifting, carry the wings out of the case and place them on the ground. This wing is being turned over so that the landing gear is on the underside for convenience later on in assembly. After both wings have been taken out, the other parts in the wing case are removed. The parts from the wing case are laid out in orderly fashion, and the crew chief is now ready to direct the construction of the platform on which the plane will be assembled. This platform is built entirely out of the material that makes up the two shipping cases. The first essential is a plot of firm, flat, and level ground. On this is placed one of the sides from the fuselage case with the flat side up. 8 feet from the front of the platform and on each side, a slot is cut for wheel clearance needed later in assembly. This slot is 30 inches long and 6 inches deep. Now the second side is brought up and laid over the first. A similar slot is cut in this second side. The finished platform looks like this. And here it is in diagram. Let's see how it's built. Here are the two fuselage case sides nailed together to form the base of the platform. Now comes the end of the fuselage case and the top of the wing case. Then comes a side from the wing case. And on the same level, a fuselage end. The remaining wing case side and the two ends from the wing case are laid on top and nailed in place. This leaves a space toward the back of the platform, which is built up by nailing together 3 2x4s taken from the wing case stringers and laying them lengthwise like this. The top of the fuselage case becomes the top layer of the platform. A diagram similar to this is reproduced in the instruction manual and should be followed in detail when the platform is being constructed. At this point, the crew chief is ready to direct the transfer of the fuselage onto the platform. If the level of the trailer bearing the fuselage is higher than the platform you have built, wheel pits of sufficient depth should be dug to bring trailer and platform to very nearly the same level. The truck bearing the fuselage is slowly and carefully backed up. Keeping it always in exact line with the platform. The prime mover is disconnected. A tow line is fastened around the entire bottom of the fuselage case. And by using the prime mover, the bottom of the case with the fuselage itself is eased squarely off the trailer and onto the assembly platform. Steady. Steady there. Just a bit more. Pull it right to the edge. Okay. Now, exactly at the back end of the shipping brace, the 10-inch section of floorboard is removed from the fuselage case bottom. Then a 10-inch section is cut out of the exposed 4x6 beams on each side. These cutaway sections, like the slot in the base of the platform, are important later in assembly. It is also necessary that the rear members of the shipping brace be removed. These members have been bolted and lightly welded in place. The bolts are removed and the weld is broken. That concludes the construction work. The crew chief can now begin to direct the actual airplane assembly. First, the engine cowling is taken off. This goes quickly if at least 4 men are assigned to the job. Now the engine must be cleaned. Kerosene or other suitable solvent may be used in removing the anti-corrosion compound sprayed over the engine before shipment. The carburetor and lower cylinders should be drained of any oil or moisture which may have accumulated. Also, the spark plugs and connecting harness must be installed. These procedures should be done in accordance with instructions found in Technical Order number 02-1-1. While this is being done, the protective tape and other coverings are taken off to expose all openings and fittings of the fuselage, wings, and all other parts. After complete inspection of the work that has been done on the engine, the cowling may be replaced. During shipment, steel braces have supported the weight of the airplane. The braces are connected to these wing hinge or pin connections. The weight must be released and transferred to these steel resting pads. This is accomplished by turning up the jack screw just 2 or 3 turns. This is enough to relieve tension on the master bolt. Then, the master bolt, which has actually carried the full weight of the plane, can easily be removed. The direction of the jack screw is then reversed. It is turned down until the weight settles on the steel resting pads. Now the hinge bracket may be removed. The hinge is then free and clear, and ready to receive the wing. To prepare for the wing assembly, we remove the pilot's seat to provide more working space in the cockpit. Now, caution. Both aileron control rods must be inserted now, flush with the fuselage. It will be too late after the wing is on. The crew chief checks to be sure that all wing connection drift pins, bushings, bolts, and tools are ready and on hand. When he's sure that everything is in its place, he can start to direct the actual wing assembly. It takes about 50 men to carry the wing of a Thunderbolt. Easy does it. That baby weighs over 1,800 pounds. The trick here is to line it up straight. Take it slow. Drop the wingtip just a little bit so that the bottom set of hinges can be lined up and connected first. After the lower set of hinges had been secured, the wingtip is lifted and the upper hinges are lined up. Both upper and lower wing and fuselage hinges are secured in the same manner. They are lined up with the aid of drift pins. When the hinges are in perfect alignment, the bushings are installed, always with the split side upward. A bushing inserter is used to drive the bushings through the hinges. The drift pin is forced out as the bushing is driven home. When all the bushings are in place, the men can ease off a few at a time so that the support they have been giving the wing will be released gradually. Next, the tapered bolts are inserted. The heads of these bolts should always be facing each other, pointing toward the inside of the wings. tap and tighten very carefully. Finally, the bolt is brought to correct tension with a 2-finger pull on an 8-inch wrench until at least 3 threads are visible on the end of the bolt. Once both wings are on, we are ready to make all wing root connections, except for the cables and control rods. This requires a thorough understanding of the connections to be made and their location. Since these connections are in very tight quarters, let's look at an animated diagram. Here are the connections to be made at the left wing root. The fuselage is here, and the wing root here. Here are the connections which are found in both wings. The flap hydraulic lines, the cannon plug, the aileron control rod, the landing gear and brake hydraulic lines, the uplock cables, and the gun heater tube. Now let's see the connections found only at the left wing root. They are the aileron trim tab cables, the static and pitot airspeed lines, and the oxygen line. Here's the situation on the right wing. In addition to the connections you see here, which are common to both wings, we have the fuel vent and the cockpit air scoop. Remember, at this point we make all connections except the control rod and cable connections, which should not be made until after the landing gear is down. In preparation for lowering the landing gear, a pit must be dug under each wing in line with the path that the wheels will take. This pit will have a maximum depth of about 1 foot at the point where the gear is fully extended. To lower the gear, wires which were attached to the uplock cables for shipping purposes are pulled at the wing root. The gear will now extend. Here is the reason we cut out that section of the platform. It would have obstructed the passage of the wheel. Notice, too, that the pits are dug quite close to the platform. In order to bring the gear down to the full downlock position, it is necessary for 2 men to get behind and push. When the downlock position is reached, an audible click is heard. With the necessary access holes now available, the uplock cables, the aileron control rods, and in the left wing, the aileron trim tab cables can be connected. Let's see what goes on inside that wing he's reaching into. To connect the uplock cables, the ends of the cables from the fuselage are drawn into the wing. The short cable from the fuselage is connected to the long cable in the wing through this access hole. The long cable from the fuselage is connected to the short cable in the wing through this hole. These connections are made with the turnbuckles, which are drawn up to a tension of 25 to 30 pounds. On the back side of this spar is a micarta guide block, which we see here. The cables are threaded through this block. Now, the aileron control rods. There's an access hole in the cockpit floor here. By reaching down through this hole, we can secure the rod with this bolt, washer, and elastic stop nut. In the wing, the same procedure is followed by reaching up through the access hole and making the bolt, washer, and nut connection. Here we see a closer view of both connections. the fuselage connection, and the wing connection. The trim tab cables remain to be connected. Here is the left wing. Here are the cables running out through the wing. By reaching down through this access hole in the top of the wing, connection is made by means of a turnbuckle. Tracer wires attached to the ends of the cables aid in pulling the cables to the points of connection. The long cable, pulled through by tracer wire, is connected to the chain by reaching up through this access hole. At this opening, reach in and install the pulley guard with a clevis pin and cotter pin provided. Here is a closer view of the pulley guard, showing where the clevis pin is inserted. A safety wire, which has been fastened around the chain, is now removed, and the cable tension is adjusted to 35 pounds. With all wing connections now complete, the next step is to make preparations for checking out the operation of the landing gear. First, we check the fluid in the hydraulic reservoir. Pressure is then built up in the hydraulic system by using the hand pump in the cockpit until the indicator shows 1,000 pounds. The flaps and brakes are now bled according to standard technical orders. 90 pounds pressure is pumped into the upper chambers of the shock struts, putting the gauge on the valve to the lower chambers. Next, after making certain that all the switches in the cockpit are in the off position, the battery, which should be brought up to full charge, is installed. Then the crew chief is ready to direct the actual testing of the landing gear, which should be raised and lowered at least 3 times. In the first retraction of the gear, the crew chief should check to see that the inner door and strut fairings fit smoothly in the wing. The next complete operation to be checked is that of the landing gear warning light. This light should remain on while the gear is being extended and should go out when and only when the gear has reached the full downlock position. The third testing of the gear is made for the purpose of checking the operation of the transfer valve. The rear inflation valve is removed, the gauge is put on the front inflation valve, a pump is attached to the gauge, and 90 pounds pressure is pumped through the gauge into the lower chamber. The gear is retracted to the point where pressure is seen to drop in the gauge. That's enough. Then a bevel protractor is applied to the gear. If the gear is 6 degrees from vertical, or within a minimum of 5 degrees to a maximum of 10 degrees, the transfer valve is operating correctly. We can get ready now to roll the plane off the platform. To do that, we must transfer the weight of the plane from the platform to the landing gear. First, the air must be released from the lower chambers of the shock struts. The landing gear must be fully compressed and held in this position while the pits are almost completely filled in and the earth packed hard under the wheels. Now the man in the cockpit should park the brakes. The entire plane is then jacked up by pumping air into the lower chambers of the shock struts. To make the pumping job easier and to relieve strain on the pump, several men rock the plane by pushing up on the wing. The result is that the plane is lifted above the steel rest pads of the shipping brace. Once the weight of the plane has been transferred to the landing gear, the two center skids behind the shipping case bracket are sawed through, and the front section of the fuselage platform with the supporting irons is pulled forward and clear. Now we are ready to release the tail from its shipping case brace. In preparation for this, air is pumped into the tail wheel strut until the piston is completely extended. The man in the cockpit locks the tail wheel to prevent it from turning sideways. We must build a track for the tail wheel to run on. To do this, we make use of one of the stringer sections formerly used to carry the wing. It is sawed into 3 equal lengths and laid directly under the tail wheel in the manner shown here. The other stringer section is placed under the empennage jack pad. 8 men now lift the tail slightly to ease the tension on the tail shipping brace bolt. When the bolt is removed, the tail is slowly lowered until the wheel rests on the tail track. The stringer we just used to lift the tail can now be sawed through the middle, and the 2 sections placed in front of the platform to form a tail wheel ramp. The tow lines are made ready and fastened to the towing hole. Stop, not there. That's the uplock hook. Use the hole that's marked for towing. A jeep is mighty handy in pulling the plane away from the platform, but manpower can do the job if necessary. The short sections of tail track are moved progressively as the tail wheel rolls forward. During this roll-away operation, the man in the cockpit keeps a slight tension on the brakes to ensure slow, even movement of the plane. Here she comes down the ramp, looking more like a P-47 every minute. Now is the time for pre-flight adjustments and inspections of the landing gear shock struts. First, all of the air is released from the lower chambers to allow the strut pistons to be fully bottomed. Next, we remove the plug on the lower chamber to see if it contains the proper amount of fluid. If there is sufficient fluid in the cylinder, it will be found level with the plug opening. Now the strut chambers are checked for proper pressures. 90 pounds is correct for the upper, and 360 pounds for the lower chambers. With these pressures, the clearance between the bottoms of the lower chambers and the ends of the pistons should be 1 5/8 inches. To make certain that there has been no leakage in the transfer valve, the gauge is put on the upper chamber and checked again to see if it reads 90 pounds. We're moving right along now, and we're ready for installation of the tail feathers. The fin and horizontal stabilizer are treated as a sub-assembly, which is installed by means of 10 bolts here and here, and 4 bolts in the rear bulkhead here and here. When this is done, the crew will be ready to string the control surface cables. There can be no confusion in stringing these cables because before shipping, each cable has been tagged to show where it goes. After the cables have been strung, the pulleys are put in place. The elevator tab cables are connected. and the cover plates are put on. The same procedure is followed for the rudder trim tab cables. Now the trim box in the cockpit should be set in neutral. The elevator control rod is placed in the tail and into position. The forward end is connected inside the fuselage. The elevator can now be installed. On each side, there are 2 stabilizer hinge fittings and 1 trim tab universal connection. The elevator control rod is connected to the elevator. The rudder is connected at the 2 pin hinges here and the rudder trim tab universal here. The rudder cables are connected next. This can be done only after the man in the cockpit has put the control lock to on position in order to place the rudder in neutral. When all the cables, bonding, and rudder tail light have been properly connected and inspected by the crew chief, the assembly of the tail feathers is complete. The ship is now ready for the installation of the propeller. Here are the steps in preparing for propeller installation. The plane is nosed up to within about 2 feet of the platform, so the men will have something to stand on while they work. Your very first action is to remove this brush holder assembly, because the brushes would be snapped off if the propeller were put on with the brush holder in place. Out comes the inner cone. And don't forget the shim, which is right behind it. The cone and shim must be thoroughly cleaned with a suitable solvent, and also the propeller shaft. The splines on the propeller shaft and also the cone and shim are then coated with a light oil. When this is done, the shim first and then the cone are replaced, making sure that the open portion of the cone is at the top. The propeller lock nut threads are coated with the prescribed mixture of castor oil and white lead. While the shaft is being made ready, the protective coating from the propeller itself can be removed. The splines on the inside of the propeller hub are cleaned and oiled, and the slip rings are wiped clean of any oil or dirt. When both the shaft and the propeller are ready for assembly, the propeller is brought up to the plane. You need at least 10 men for this job. Under the guidance of the crew chief, the propeller is carefully placed on the shaft. The number 1 blade should be on top so that the splines will be readily engaged. Now the main propeller shaft nut is tightened with the 4-foot propeller bar. After the nut has been drawn tight, insert the locking sleeve and secure with the lock pin assembly. Next, after cleaning, the brush assembly is put in place and the brushes checked for proper clearance on the slip rings using Prussian blue according to standard procedure. The propeller hub electric contact points are cleaned and made ready to receive the power unit. The power unit itself is removed from the case and cleaned with particular attention to cleaning around the contact points. Since the power unit is set in low pitch when packed, the blades on the propeller must be set in low pitch also. When the power unit is installed, the 8 bolts are drawn up and secured with safety wire. The propeller gear housing is then greased and the speed-reducing gear housing is oiled. With the power unit cover or spinner installed, the propeller assembly is complete. Now, all of the major connections on the airplane have been made. After a thorough inspection by the crew chief, we install the fillets and secondary cowling. The pilot seat is returned to its place in the cockpit. And when the pitot tube, antenna wires, radio mast, and pilot's rear view mirror have been installed, the armorers are ready to take over, to install the guns and charge them. The job of assembly is done. The plane is towed off to the airfield runway. Here, after the plane has been fueled, the crew chief runs up the engine and makes one final check on the operation of all instruments and movable surfaces.
Ready to fly and ready to fight. This plane has been completely uncrated and assembled in the field. This simplified uncrating and assembly method is the answer to field requirements. Just as the plane itself, the P-47, answers the requirements of the fighting pilot. The Thunderbolt is in the air.
What makes a champion? A champion is an expert who can play the game or do the job just a little better than the other fellow. In a tennis match, for example, the champion generally succeeds in putting the ball where he wants it to go, while his opponent makes just a few more errors. The opponent is an expert too, and practically as good as the champion. Otherwise, he'd never get in the game against the champion. In a match of this sort, the champion may win a set by 6-love, which makes him appear to be far superior. Actually, however, he may be only a shade better than his opponent on any individual stroke throughout the match. In dive bombing, much the same relation exists between the good dive bomber and the expert. The expert, or the champ, will get the smallest average error. But every dive bomber can be good enough to hit. And in combat, a hit on the stern of the ship is as good as one in the center. There are only a few who can hit the target with almost every bomb. But every dive bomber can improve his bombing enough to hit the target a majority of the time. Dive bombing, first developed by the United States Navy many years ago, is now recognized as one of the most accurate and destructive forms of air attack. Any pilot can drop bombs somewhere near the target, but the expert dive bomber knows where his will hit. Any pilot who carefully studies and then applies the principles of dive bombing in their logical order will soon find that his hitting average is climbing up there with the rest of the experts. Dive bombing is simply a matter of flying the airplane smoothly in a dive while making the proper allowances and corrections so that the bomb will hit the target. But in dive bombing, so many things happen so quickly, with so many possible variations, that some repetition and overlapping are necessary to show all the important fundamentals. In this film, we will see a generalization of the fundamentals, and in the films that follow, we will see the detailed application of principles as they affect different phases of the practice and combat dive. In dive bombing, the airplane is the gun. The bomb is the bullet. There are certain factors which must be considered in dive bombing, just as there are in ordinary shooting. Let's consider them one at a time. Let's assume we're in a stationary airplane over a stationary target with no wind and no air resistance. A bomb is released. As gravity acts upon it, the bomb falls at a constantly increasing rate of speed. During each second it falls, the bomb speed is increased about 32 feet per second until the bomb hits the target. Let's repeat the scene and watch it more closely. The bomb falls 16 feet the first second, approximately 48 feet the second second, 80 feet the third second, and so on until it strikes the earth. Under the conditions we've assumed, the bomb will fall straight down and hit the target. Now, let's assume that instead of being stationary, the airplane is in horizontal flight. Again, we release the bomb. Gravity still pulls the bomb toward the earth with the same acceleration as before. But now the bomb has the airplane's forward speed also. Since two forces, gravity and forward speed, are acting on the bomb at different angles, the bomb has to move in two directions at the same time, down and forward. As the force of gravity accelerates the bomb, it follows a curved path called the trajectory. Because of the curve of the trajectory, it's necessary to release the bomb some distance short of the target in order to score a hit. If gravity and the airplane's motion were the only two forces acting on the bomb would always strike the ground directly under the airplane. But the path of the bomb is also affected by a factor known as trail. Trail is caused by air resistance, which slows the motion of the bomb and makes it fall short. These three major factors working together, forward speed, gravity, and air resistance, make it necessary to correct the aim to hit the target in range. So, in horizontal bombing, we must allow for the pull of gravity on the bomb, the speed of the airplane, and the effect of air resistance in finding the proper position for the release of the bomb. If we release too soon, our bombs will undershoot the target. If we release too late, our bombs will overshoot the target. If we release at the right time, we hit the target. So far, we've been considering an airplane in level flight. Now let's put the airplane in a vertical dive over the target and see what happens. The speed of the airplane, the pull of gravity, and air resistance are now working in the same direction. So, by aiming the airplane at the target, we have eliminated any need for correcting the range. The bomb will hit where we aim, whether we release early or late. This ability to hit by flying the airplane at the target and releasing the bomb whenever our aim is on is the foundation for dive bombing. You will see later that we can hit where we aim without diving vertically, and that a shallower dive is actually better than a vertical dive for practical purposes. To keep the bombs from falling under or over the target, we must be aimed correctly for range, whether in a shallow dive or a steep dive. In dive bombing, we correct the aim in range by pulling or pushing the stick, just as we do in horizontal flight. This raises or lowers the line of flight to the proper point of aim in range. It is harder to correct for range in a shallow dive than in a steep dive, because the same error in estimating dive angle makes a larger error in range. On the other hand, it's easy to correct for range in a steep dive because the same amount of error makes a much smaller error in range than in a shallow dive. Furthermore, the same amount of error in estimating our release altitude will cause a greater range error in a shallow dive than in a steep dive. In a shallow dive, the bomb falls much farther from our point of aim than it does in a steep dive. Estimating this range correction introduces an error. We have only the size of the target to help us estimate our corrections. In making large corrections, this leads to error. It is also much harder to estimate the dive angle of a shallow dive correctly so that our expected error is still greater. Let's make a dive on a windless day. If we reach release altitude at a normal dive angle with our line of sight on the target, the bomb will hit the target. Gravity causes the bomb to land short of the line of flight. The sight is bore-sighted, so the line of sight is below the line of flight. If this is done, the bomb will hit our point of aim when we release in a normal dive. If, however, we're diving the airplane toward the target and find that we're too shallow, we must change our line of flight or the bomb will fall short of the target. Of course, on nearing release altitude, we can pull up the nose, raising our line of flight. This corrects our bomb toward the target. But it does not change our vertical angle with respect to the target. as we change the line of flight almost instantly when we pull up the nose. This correction changes the bomb's path because the bomb is affected by the airplane motion which is along the line of flight. The bomb lands far short of our line of flight and the line of sight because of the large effect of gravity in a shallow dive. The range correction is so large that it cannot be estimated accurately. Let's see what happens if we steepen the same dive to the normal dive angle as soon as we see we're too shallow. Now, although the bomb will land on the line of sight, it is far short of the target. As before, we can pull up the nose, raising our line of flight and line of sight over the target to correct for range. But now our vertical angle from the target is even less than before. And our range correction is still larger. We are worse off than we were to begin with. Let's repeat the same dive and try to correct it once more. This time, we'll pull the nose up whenever we see we're too shallow. If we release our bomb with no correction, it would land even further short of both the line of flight and line of sight than it did in our original dive. But by diving shallower, we have raised our line of flight far over the target, so that the bomb will land over the target even though it's further short of the line of sight. However, our vertical angle from the target is now correct, and as we near release altitude, we correct our line of flight by pushing the nose over and putting our point of aim on the target. This correction puts us in a normal dive so that the bomb will land on the point of aim. So, if we start a dive incorrectly, we can still release in a normal dive. If we find ourselves in a dive that's too shallow, we should raise the nose, steepening the vertical angle from the target in order to reach release altitude near the normal dive angle. The bomb will land so near the point of aim that range correction is easy to estimate. On the other hand, if we find ourselves in a dive that's too steep, we should push the nose over to correct the vertical angle from the target and again reach release altitude so that when we make our range correction, we are in a normal dive. Now that we've considered the problems of range, let's consider the problem of deflection. We must keep the bomb from falling to either side of the target, as seen by the pilot. We correct for deflection by turning the airplane right or left toward the target, because we must correct the line of flight of the airplane. Assume that the airplane is in a shallow dive. A small amount of turn will correct a large error in deflection. Now let's aim the airplane at the ground in a steep dive. We see that to make even a small correction in deflection, the airplane must be rotated almost 90 degrees. Turning an airplane in a steep dive is difficult. If we apply much rudder in a steep dive, the airplane skids instead of turning. A skid like this may skid the airplane just enough to point the line of sight directly on the point of aim. Because we can hold the line of sight on the point of aim, we get the false impression that the airplane is diving toward the point of aim. This is an illusion, because even the heaviest skid gives the airplane very little horizontal motion in a dive. Because of this, it's important for us to remember that in a steep dive, we turn the airplane with much more aileron than rudder, like this. We have seen that it's easier to correct for range in a steep dive and for deflection in a shallow dive. We can't do both at the same time. The only thing we can do is compromise and make our dive somewhere between the steep and the shallow dive. Such a compromised dive is called the normal dive, in which we release our bomb in a dive angle of about 65 degrees. The normal dive starts shallow enough so that deflection can be corrected with a relatively small turn. The normal dive angle ends steeply enough so that corrections for range are easily estimated. Experience has shown that a dive near this angle is best for bombing targets when we have to concentrate on both range and deflection. There are some targets, however, such as bridges, on which we can concentrate on one aim factor at the expense of the other. For instance, here we can approach in a shallow dive up or down the bridge and concentrate on correcting deflection. The length of the bridge will allow plenty of margin for normal range error. Or we can approach in a steep dive directly across the bridge and concentrate on correcting range, because the length of the bridge will allow plenty of margin for any normal error in deflection. In the previous examples, we assumed that the airplane was flying through still air. Actually, still air is the exception rather than the rule. Therefore, in dive bombing, we must make accurate allowances for the drift of the wind. Assume we are in a dive and have an accurate bead on the target in both range and deflection. Now let's add the factor of the wind blowing sidewise on the airplane. This horizontal wind will drift the airplane sidewise during the dive, moving our line of sight off the target. Let's repeat the dive and allow for this drift, so our line of sight is on the center of the target at release altitude. When we release the bomb, however, we find that it retains the airplane's sidewise motion just as it does the airplane's forward motion. So the bomb is now falling sidewise too. Because this sidewise motion will carry the bomb off the target, we'll still fail to hit. Therefore, we must allow for the drift of the airplane before release altitude, plus the drift of the bomb after release, in order to make a hit. If the wind with which we're drifting during the dive remains constant, it is the effective wind. If the wind with which we're drifting during the dive varies, the wind drifting us at release altitude is the effective wind, since this is the wind drifting the bomb as it falls. We'll see in a later film that the wind about 500 feet above release altitude is the effective wind. With knowledge of the effective wind, the wind affecting the airplane at release altitude, we'll be able to select our tentative point of aim on a stationary target far enough upwind from the target to allow for the bomb's drift after release. We must also allow for the drift during the dive. If we fail to allow for this drift, we must continually turn to keep on the tentative point of aim. In moderate winds, the turn is so sharp that it becomes difficult. In strong winds, it's impossible. So we select a pushover aiming area far enough up the winds through which we dive to allow for the drift to the tentative point of aim. We push over on that area. As we dive, the moving point of aim travels toward the tentative point of aim. We can easily make small corrections in our dive up to the point of release. So by the time we reach release altitude, we should be aimed in deflection at the tentative point of aim. Just before reaching release altitude, we go to our sight and correct our aim in range. This final correction gives us our release point of aim. In the previous examples, we've assumed that the targets have been stationary. In most instances, however, dive bombing targets are moving to get away as fast as they can. Now let's assume that our range, deflection, and wind are all taken care of, but that the target is moving. We drop the bomb and miss because, in the few seconds it took for the bomb to fall, the target has moved out of the way. In order to hit a moving target, we must figure out how many feet the target will move forward while the bomb is falling. Then we must aim that distance ahead of the target center so that the target and the bomb will meet. Let's try again. This time we'll aim ahead of the target. We release the bomb. And bang! We score a direct hit. There's nothing haphazard about dive bombing. After the basic principles are understood, the rest is the practice that makes perfect. Maybe we won't put all the shots down the stack, but we can put them where they count. Let's review the steps to take. First, we identify the target. Then we pick our point of aim and start our approach. We enter the dive, allowing for the drift of the wind and the motion of the target. We make our smaller corrections to get the final point of aim. We release, pull out, and
of this film is to introduce you to tactical day fighter and fighter bomber operations, and to show you how they are employed in combat. The instructor is showing the class the place of the Tactical Air Force in the theater of operations.
With that in mind, gentlemen, we come to the purpose of this indoctrination course on tactical air operations. Very shortly, most of you will be assigned to fighter bomber and day fighter wings in combat. It is my purpose here to explain the overall tasks which must be accomplished by a tactical air force. The basic combat functions performed by a tactical air force are counter-air operations, interdiction, and close air support. These tasks may be conducted concurrently or the emphasis shifted as required. Now let us remember that the successful conduct of theater air and surface operations is dependent upon the attainment of an acceptable degree of air superiority. Yes?
Sir, I'm Captain George. Is the main objective of counter-air operations the attainment of air superiority?
Not altogether. Air superiority merely indicates a satisfactory control of the air which permits surface and air action in the area of operations without unacceptable restriction by enemy air forces. However, the primary objective of counter-air operations is the overall destruction or neutralization of the enemy's air power. When this has been done, naturally you possess air superiority. The targets for counter-air operations generally fall into these categories: aircraft in the air or on the ground, air bases, personnel, and installations supporting the enemy capability. As to the second task, interdiction has the objective to destroy or neutralize the enemy's potential before it can be brought to bear against our forces. It also restricts the mobility of the hostile forces by disrupting their lines of communication and transportation. The destruction of railroads, roads, and pipelines will deny the enemy the ability to provide supplies and reinforcements and will impair his movements. Transportation centers, forwarding points, supply and storage facilities are important interdiction targets. Our attacks on his repair and modification centers further limits the enemy's ability to replace his battle losses. From time to time, fighter-bomber forces are called upon to provide close air support. The objective of close air support operations is to assist the surface forces by aerial delivery of firepower against hostile surface targets in the immediate battle area. In close air support operations, detailed coordination is required with the fire and movement of surface forces. There are three general types of close air support targets: concentration of enemy troops, materiel, and fortified positions. You have a question, Major?
Sir, I'm Major McManus. With the detailed coordination required in close air support operations, how is the ground fire coordinated with the airstrike?
A good question. Close air support strikes are performed under the direction of a forward air controller. He observes the strike from his position in the front line area. This man has communication with both the flight leader and the fire support coordination center. He is responsible for the coordination of the air attack with ground fire, to include directing simultaneous air and ground fire against selected enemy targets. This officer is an experienced fighter-bomber pilot who is selected for his experience in close air support to represent the Tactical Air Force commander. Again, gentlemen, when you are assigned to your combat wings, these are the tasks you will be called upon to perform: counter-air operations, interdiction, and close air support. Now there are a couple of topics that I would like to review with you once more.
3 months later, replacements arrive in the combat zone for the fighter-bomber unit. The mission of the fighter-bomber is to attack and destroy enemy air and surface forces, transportation systems and installations, and when required, conduct such operations in close coordination with friendly ground forces. The day fighters receive replacement pilots. The mission of the day fighter is to visually intercept and destroy enemy aircraft in the air and to provide fighter protection for friendly air and surface forces against enemy aerial attack. Those are the missions of the fighter-bombers and day fighters. Now let us see how they operate in combat. Preparation for the daily activity of a fighter-bomber or day fighter group in combat begins the night before. That is when operations orders from Tactical Air Force Headquarters arrive at the day fighter and fighter-bomber bases. The operations order for this particular fighter-bomber wing directs counter-air, interdiction, and close air support missions in conjunction with a planned breakthrough by friendly ground forces. All squadrons are involved. The first step is to prepare detailed plans for the day's operations, such as mission assignments to each squadron, briefing times, aircraft required, and ordnance loads. Prior to each mission, pilots are assembled for detailed briefing. The ground liaison officer presents the general ground situation, indicating the bomb line, color codes of the day, and passwords. For close air support missions, his briefing includes objectives of the ground forces, lines of departure, time of the offensive, and other information which will assist the pilots in their mission. The intelligence officer briefs the pilots on target identification, flak concentrations, best routes of approach to the target, also escape and evasion tactics. The weather officer predicts the weather over the mission routes and target areas, the winds aloft, probable surface winds over target areas, cloud formations, visibilities, icing conditions, and any other weather phenomena of operational significance. His briefing may be augmented by last-minute weather reconnaissance information. The Group Operations Officer explains the mission in detail: start engine times, routes, time on target, deception measures, and navigation data. Particular emphasis is placed on results to be achieved by the attack. During the day, fighter bombers will be committed to a counter-air strike on an enemy airfield, while other fighter bombers will strike an interdiction target at a railroad marshalling yard. Still others will provide close air support for the planned ground offensive. At the end of the presentation by the group staff, the group commander closes the briefing with his final instructions. Now, more detailed briefings will be held at each squadron. This is Robust Squadron, which will participate in the counter-air strike on the enemy airdrome.
Well, as usual, I'll be Robust Red leader, and I want us all to make good our start engine times and get out on the runway together.
The squadron commander explains in detail how he expects the squadron to perform: start engine time, taxi out, takeoff, join up, radio discipline, formation and routes, altitude, tactics, emergency procedures, and all special details peculiar to this mission. However, briefing does not end with the squadron commander, for the flight commander is responsible that each of his pilots understands exactly his part in the mission. Loaded fighter bombers marshal on the runway and take off. The mission is under surveillance of the Tactical Air Control System. Through this system, the Tactical Air Force commander may advise of reported enemy air activity, provide navigation and rescue assistance when necessary, and divert his forces should the situation require. Upon takeoff, the fighter bombers assume combat formation, except when weather penetration is required. Alert for enemy air attack.
Colgate Control, this is Robust leader. Inbound to target is brief. Roger, Robust. This is Colgate Control. Proceed as brief.
Meanwhile, the day fighter has been preparing to take its place in the day's action. The day fighters will independently and in conjunction with the Tactical Air Control System visually intercept and destroy enemy aircraft in the air. They will provide fighter screens and cover for the protection of friendly aircraft and surface forces against enemy attack. From the same operations order, the day fighter units have planned their missions for the day to prevent any enemy interference with the fighter-bomber effort or the ground offensive. The same process of detailed briefing by the group specialists, the squadron commanders, and flight commanders has been employed to assure intimate knowledge of all phases of the mission by the day fighter pilots. The day fighters start engines, taxi, and take off with split-second timing to sweep the area ahead of the advancing fighter bombers. The day fighters have been directed to establish a screen between the target and an enemy airfield complex from which opposition is expected to rise. They will also cover the withdrawal of the fighter bombers. They report in to the Air Control Center. Then, under strict radio discipline, the day fighters begin their search of the sky, but are alert for reports of enemy air tracks from the Tactical Air Control System.
Grundy, Red leader, Red 3, bogeys, 10 o'clock low. Roger, Red 3. I got them. They're bandits. Red 3, take the right.
the day fighters continue to sweep the area throughout the fighter-bomber strike. The fighter-bombers begin letdown and position themselves for attack.
Robust Red Leader going in.
Bursts from the guns on the way in may help to discourage the flak batter.
Red Leader here. Rocket switches, Robust. There's some aircraft in those two big hangars. Red Leader here. Last pass, Robust. Grundy Leader, this is Robust. Off the target. Set course for home. Roger, Robust. Grundy Leader here. We'll follow you out.
As another major task of tactical air, interdiction has the objective to destroy or neutralize the enemy's potential before it can be brought to bear against our forces. While the counter-air mission is in progress, fighter-bomber aircraft are dispatched on an interdiction mission to attack a railroad marshalling yard supporting an enemy buildup. The ordnance load will be 1,000-pound general-purpose bombs. Upon completion of the primary mission, the aircraft will perform an armed reconnaissance from the target south to Purple 10 on the enemy's main supply route. Additional ordnance will be at the wing commander's discretion. Once airborne, the interdiction mission is monitored by the Tactical Air Control System.
Colgate Control, this is Cherokee Leader. Inbound to target as briefed. Over.
Roger, Cherokee. Colgate here. Cleared inbound to target as briefed.
The interdiction strike will proceed along a pre-briefed route to avoid areas of intense flak. Routing has been selected to secure maximum surprise upon arrival at the target. A target, such as the railroad marshalling yard, may be pinpointed by relating it to some prominent geographical checkpoint, and then by following some well-defined route to the target itself. Having completed their attack, these aircraft will perform armed reconnaissance from target south to Purple 10 on the enemy's main supply route. Armed reconnaissance is accomplished by seeking targets of opportunity along a predetermined route or in a designated area. In this phase, the fighter-bomber pilot is both hunter and killer.
Cherokee, Red Leader from Red 2. I think I've got a couple of trucks spotted. pass at him and I'll follow you.
The objective of close air support operations is to assist surface forces by aerial delivery of firepower against hostile surface targets in the immediate battle area. Aircraft are dispatched for a close air support mission in red sector: ordnance load, napalm, rockets, and guns. 8 aircraft have been retained on ground alert in anticipation of a requirement for immediate close air support of an Armored Division offensive operation Linebuster. Throughout the mission, this flight will also be under the direction of the Tactical Air Control System. In the target area, close air support missions such as this are conducted under the visual control of a forward air controller. As pointed out earlier, the forward air controller is a combat-experienced fighter-bomber pilot, selected for his experience in close air support. He represents the Tactical Air Force Commander.
Golf ball, this is Robust X-ray over Point Boxer. Do you have me in sight?
Roger, Robust X-ray. This is Golf Ball. I have you. How do you read me?
Robust X-ray to Golf ball. We read you loud and clear. Over.
Robust X-ray, begin an orbit to the left. Your target is a heavily fortified artillery position west of the lower ridge line, 4,000 yards forward of our nearest friendlies.
Roger, Golf ball. We have it. Mark the target.
Marking round is on the way. Splash. Do you see the burst of white smoke just east of your ridge line?
We've got it, Golf ball.
Your target will be about 500 yards west of the ridge. Can you see it?
Roger, I've got it. X-ray flank, roger if you have the target. X-ray rolling in.
As X-ray flight is cleared back to base, another fighter-bomber flight on ground alert has been scrambled to attack enemy tanks, which are holding up the advance of the armored offensive. Speed is essential to an armored advance. For that reason, close air support and the firepower of the ground forces must be closely coordinated. Once the fighter-bombers are over the armored column, the forward air controller takes over and directs the flight to the enemy tank. This attack is made possible by the flexibility and mobility of air power under centralized control. Although in this instance the aircraft held on ground alert are now being used to assist an armored advance, they could have been used anywhere in the theater of operations, either to assist surface forces or to repel an enemy air threat.
Unidentified track just entered range, bearing 338.
As the operations order directs, 8 day fighter aircraft are on ground alert from dawn to dusk.
Hello, Thoroughbred. This is Echo. Over. Roger, Thoroughbred. Scramble fist fight. Report to Echo over Point Victor. 20,000. Over.
Echo from fist fight over Point Victor at Angels 2-0. Over.
Roger, fist fight. This is Echo. We have bogeys. Heading 195 degrees. Vector 340. Angels 45. Over.
Echo from fist fight, roger. 340. Angels 45.
Fist fight from Echo. Vector 300. 1
Roger, Echo 300, 110.
This by Echo here. Vector 280, 60 miles.
Roger, 280, 60 miles.
Echo to Fistfight. Vector 240. Bogies at 2 o'clock, 12 miles.
Fistfight leader from 3. 4 bogies at 2 o'clock low. Roger, 3. Echo from Fistfight. We've got him in sight. Clean him up, Fistfight. Hang on, 2. Fistfight 4 leader here. Watch him, boy. He's coming around on you. Suck it in. Okay, keep turning. I got him. No sweat. I'm a clear, Red 2.
You're clear, Red Leader.
Let's go home, Fistfight.
Fuel is a critical factor in jet aircraft operations. Flights returning from combat missions are usually low on fuel and must perform precise navigation and cruise control.
Fistfight leader here. Back to 91%.
Formations returning from a mission normally check out with the agencies they have worked with, giving spot reports on the results of missions or on new targets in enemy territory.
Echo from Fistfight, we got 1 kill, 1 damage. Other 2 headed north. Outbound with 4.
As the day progresses, mission after mission is checked off the board. Flight after flight comes in. Each returning aircraft is carefully checked for battle damage, mechanical failure, and malfunction, and is made ready for the next day's operation. In the debriefing, intelligence gets a detailed report from every pilot of what happened on the mission. Information from all missions will be evaluated and passed quickly to higher headquarters, where it will be considered in planning future combat operations. Mistakes, errors of judgment, and breaches of teamwork are discussed and corrections directed by the flight leaders. As the fighter bombers and day fighters complete their portions of the day's operations order, the night intruders are already taking off to continue the unremitting pressure on the enemy.
Turn that up. Roger. 2 down, 1950. We're all down, Colonel. That's good, Joe. I think I'll check and see how the day fight is made out. Yes, sir. Let me know when the ops order comes in. Yes, sir.
are labels for misery and destruction. The common label for this is World War II, subhead, Japan. Another name for it, one that might describe it better, is Strategic War Number 1. Look carefully. What you are seeing marks the beginning of a new era in the ancient annals of war. For here we view the aftermath, the end result of the first war in which a nation submitted to unconditional surrender with its armies still intact and ready to fight. And where was this army? It was off stage, waiting for an invasion that never came, while a new kind of invasion struck behind it, cutting out the very heart of the nation's life. Etch deep in your memory the nature of this new kind of war, because if ever there is another war, it will be won this new way. It will be won or lost by strategic attack. Just what is strategic attack? The support of military forces in the field requires a constant stream of supplies which flow from the great industrial complexes. These production centers are the heart of any war effort, and the lines of supply are arteries through which military forces are equipped for combat. In military terms,
strategic attack is an attack with effective force directed at the heart of an enemy's war-making power, at the vital points in its national structure. Its purpose is to destroy or paralyze both the ability of that enemy to fight and his will to fight.
General Eisenhower has put it this way.
Our national structure is composed of extremely specialized elements whose continued operation is dependent on the efficient functioning of all other elements. Even a minor panic or local paralysis is a serious matter. Many million urban dwellers who raise none of their own food would starve within weeks if the transport system were broken. Heavy industry would shut down if Pittsburgh, Birmingham, and the Gary areas were destroyed. Our national life would be crippled if Washington, New York, and a few other centers were subjected to sudden attack. We could scarcely carry on if bacteria should destroy the grain crop of a single year.
Yes, the ability of any nation to wage modern war depends on the complex interrelationship of its component parts, its natural resources, its industry, its transportation, its public utilities, its network of communications, and its manpower. Each of these is dependent on the other. Stop the functioning of one of them, and the others will begin to wither and die for lack of nourishment. Imagine, if you will, an extreme example of this principle. It is conceivable that the entire supply of a nation's oil resources and storage facilities might be located in 2 or 3 centers. Oil and its byproducts are essential to the efficient functioning of virtually every piece of mechanized equipment used in warfare, as well as many vital elements in the civilian economy. The destruction of these few production centers would effectively cripple that nation's ability to wage modern war. You would defeat that nation with a few decisive blows, just as surely as if you destroyed its armies in the field. That is strategic attack. 1942, the war with Japan was proceeding along the line of traditional warfare. The Japanese, with years of secret preparation behind them, had struck fast and ferociously, and we were forced to retort in kind. They had reached out far, seized vital positions, and set up strong defenses throughout two-thirds of the entire Pacific. Our first thought was to keep the Japs from knocking out all our Pacific Island bases, to stop his expansion while there were still footholds from which to launch our counteroffensive. This meant the tough man-to-man, hand-to-hand fighting of past wars. With characteristic thoroughness, the Japs were imitating everything they'd been able to pick up from other nations on how to fight a war. Their tactics were strictly according to the textbook, the very latest ones, too. Japan had built a kind of Maginot Line protecting her empire. By every well-known, honorable, old-fashioned rule, we should have battered away at that line, winter and summer, on land and sea, until one or the other of us ran out of soldiers, sailors, and ammunition. But our military men, who were learning much in breaking the Nazi war machine, were writing a new book. Its theme, the art of striking around, under, or over your enemy's line of defense. In this case, directly at the heart of the Japanese economy. But to wage strategic war, it is first essential to know the nature of your enemy, the vital elements which form the backbone of his national life. Before the war, most of us had a somewhat misleading idea of Japan and the Japanese. We thought of Japan merely as a picturesque little country, filled with cherry blossoms and dotted with beautiful temples and ornate Shinto shrines. The Japanese people, we understood, were exceptionally well-mannered. They made a fetish of politeness. They did a great deal of bowing. We were fascinated with the quaint way they arranged flowers and drank tea. Tea drinking was quite a complicated matter. But then, of course, they had been working hard at it for several thousand years. Practically all of their houses, we thought, were made out of bamboo and rice paper. Japan, through the centuries of isolation from the rest of the world, was little known to us, and we were inclined to underestimate her ability to build a modern war machine. We know now this was not the real nature of Japan. Fortunately, as the war clouds gathered, our military planners were engaged in the task of piecing together the true picture of Japan's military strength. The assembling of such a picture, from bits and pieces of information gathered from 1,000 varied sources, is the job of our intelligence system. Not many beautiful, mysterious, secret agents of old-time warfare. Much more likely, a worried scientist or technician with tired eyes. He's less interested in the secret plans of the enemy's fortifications than he is in determining how many electric generators they can afford to lose and still be able to fight a war. He's looking for soft spots in the enemy's industrial system. A slight shortage of manganese, or chrome, or kilowatts can mean more to him than a dozen divisions on the march. If the nation's steel supply is cut off from behind, those divisions won't march far or for long. What, then, was the real nature of Japan? Let us analyze what was going on behind the silken curtain. First to be considered about Japan was its position as an island empire. Important because the Japanese were obliged to import almost all their raw materials to feed their war economy, a serious weakness in time of war. It gave them extended lines of supply that had to be protected. It gave us a first-class strategic target. That was only the beginning. Japan entered the war with 6 million tons of shipping. She added 4 million to this during the war, some of it from owners who entered the Japanese co-prosperity sphere, dead or alive. The Japanese army at its peak totaled about 5.5 million. A well-armed force, skillfully trained and seasoned through years of combat with the Chinese. Japan's navy was third largest in the world. She began the war with 381 warships and built 816 more. 2 were battleships, bigger and more powerful than those of any other nation. At the beginning of the war, Japan's frontline combat strength in aircraft totaled some 2,600 planes. Production later rose to a peak of 2,500 a month. The orientation of the Japanese economy toward war began as early as 1928. By 1940, production was up 500%. Her major war industries were erected from almost nothing. Bamboo and rice paper? The fact was, parts of her cities were more strongly built than our own. And no wonder. Periodically visited by earthquakes, the Japanese had investigated and put to use every modern scientific method of building shock-proof structures. Japanese industry became westernized after the First World War. She learned how to mass produce. She not only mass produced cotton and silk, toys and machinery, but guns and tanks and planes, until over half of her entire industrial output was devoted to war production only. This, then, was Japan at war, a modern nation with a powerful and efficient war machine, an economy engaged in all-out production to support her war aims. But strategic attack requires more than an overall picture. It requires a detailed analysis which will expose the weak points in the enemy structure and bring into focus the most critical targets. They're not unlike the strategic targets in our own country, which would certainly invite the attention of our enemies in the event of a future conflict. Shipping. Japan's merchant shipping fleet was not only a key link in the logistical support of her armed forces, but also a vital factor in her entire economic structure. Japan's basic objective in provoking the war was to obtain the rich resources to the south of her. It was clear that by cutting her lifelines to these vital resources, we could severely impair Japan's ability to sustain her war industries. Railroads. Much of Japan's coastal and inter-island traffic depended on her railroad network. The successful strangulation of these would reduce Japan to a series of isolated communities, incapable of any sustained industrial production, incapable of moving food from the agricultural areas to the cities, incapable of rapid, large-scale movements of troops and ammunition. Steel. Japan had built up a large stockpile of iron ore, pig iron, and scrap iron before the war. She had her Garys and her Pittsburghs, too. Massive units with a long head start in making steel for war purposes only. Oil was of critical importance. Before the war, the Japanese stored up all the oil they could possibly get their hands on. They entered the war with reserves of 43 million barrels. Industrial energy. The major facts of Japan's basic power position were well known to the Allied intelligence. Seriously deficient in natural gas and petroleum, Japan was almost entirely dependent on water power and coal for her industrial energy. It was estimated that about 2/3 of the total energy consumed by the Japanese war economy in 1943 was derived from coal. Munitions, the end product of a war economy. Having prepared to take the initiative, Japan in 1941 had progressed further toward converting her industries to war production than had the United States. Even so, they were far from their peak. Production of military supplies in 1944 was over 3 times the rate in 1941. Manpower. The cities and towns of Japan were highly organized, integrated parts of the industrial economy. From these centers poured the manpower to work hard and long in the large war industries. Here was the source of mass labor, a most vital element in a nation's war economy. Here, too, were centered the countless small workshops peculiar to the Japanese industrial complex. From these feeder plants, employing less than 100 people, came a steady stream of component parts, cog wheels, an aircraft brace, a rifle bolt, pouring into the larger assembly line. Yes, the urban areas of Japan pulsed with the energy of a nation committed to total war. Morale. Japan's food position at the outbreak of war was favorable by Japanese standards. In fact, when war came, the people were better fed than at any time in their history as a modern state. Courageous and hardworking. Women and children toiled in the fields along with the men. They tilled land that other nations would have left idle. Their methods were primitive, but coaxed large crops from the carefully pampered soil. The Japanese consumed very little meat. They depended heavily for the protein element in their diet on large-scale fishing. In fact, they put so great a store in the bounty of the sea that more money was spent on seaweed as a food than on meat. By comparison with United States and Western European standards, Japanese private housing was overcrowded and flimsy. However, for the most part, the average family was self-sufficient for its dwelling requirements. If a man needed a home, he generally got the basic materials and hand tools together and built it himself. These, then, were the critical points in Japan's economy: her resources, her industry, her transportation, her workers. This was the heart of the enemy's war potential. But strategic targets alone are not enough. There's another essential element in waging strategic warfare. You must have strategic weapons, not the commonplace weapons of old-fashioned warfare, but weapons that meet 4 rigid specifications. 1, they must have sufficient range to launch an attack on the enemy from available bases. 2, they must be capable of penetrating any and all enemy opposition organized to defend the targets upon which his war economy is based. 3, they must deliver to the target sufficient firepower, bombs, to destroy those targets. 4, they must be available in sufficient numbers to sustain the attack and make recuperation impossible. It was the acceptance of its design that signified a realization of the true meaning of strategic air power. But it takes time to build the weapons of strategic warfare. It took a long time to design, build, and deploy for combat the first B-29. It took 8 years. The war was 2.5 years old before the first units were ready to strike the Japanese homeland, and over 3 years old before the 20th Air Force had adequate bases from which it could unleash the full fury of its power. The question of what to do with our strategic air weapon once we had it was decided upon by the Joint Chiefs of Staff in Washington. Based on detailed information supplied by military intelligence, it was up to them to decide which of the strategic target systems should be attacked and what sequence in order to secure the greatest cumulative effect on the overall economy. Should we strike the Japanese airframe industry first, or the aircraft engine industry? Should we direct our strategic air force against the coke, iron and steel industry, or petroleum? Should we disrupt their rail communications, destroy their shipbuilding industry, or level their cities? What targets were we most capable of neutralizing? And what would be the predictable results on the Japanese frontline strength in the air, on the ground, and at sea? The decisions were especially difficult because there was no convincing precedent. This was the first time a nation possessed an effective weapon that could reach across oceans and battle lines to smash directly at the heart of an enemy. With the seizure of the Marianas in mid-1944 and the establishing there of bases for our very long-range, very heavy bombers, the stage was set and the curtain raised on a drama such as the world has never before seen. In August 1944, a decision was reached which set forth a general target directive. Target priorities were established, and the most potent military force in history was made ready to carry the war directly to the source of the Japanese war-making power. This is Air Force 1944 model. By no means new technological warfare, but a forerunner of what the future portends. Watch these instruments of a past war in action. In accordance with the Joint Chiefs of Staff directive, the Japanese aircraft engine industry was selected as the target for the first mission of the 20th Air Force operating from the Marianas. On the 24th of November 1944, 58 tons of bombs were dropped on the Nakajima factory near Tokyo, 2,800 round-trip miles from base. The crash of these bombs marked the opening of our unparalleled air offensive. Day after day, week after week, month after month, the attacks continued and gained momentum. Now the target was the Japanese aircraft industry. Now the large urban areas. Now the oil industry. Then Army and Navy arsenals. The chemical industries, aluminum processing, railroad installations. One strategic target group after the other. All with one single objective: to destroy the enemy's capacity to carry on the war. And what is the effect, the end result of 322,754,000 pounds of bombs on a nation's economy? Judge for yourself. This is what happened to the Japanese aircraft industry. In September of 1944,
Japan's production of aircraft and aircraft engines was 6 times greater than in 1941. Then came the B-29. By July of 1945, 57% of this phenomenal capacity had been destroyed. These were the famous Mitsubishi aircraft and engine plants in Nagoya. The aircraft factory was one of the largest in the world, bigger than Willow Run. Of 8 million square feet of productive floor area, 4 million square feet were destroyed. There was a special priority on the engine work. More than 90% of it was destroyed. The Nakajima Aircraft Company, largest producer of Japanese aircraft and engines, was second hardest hit. 17 attacks, 4,300 tons of bombs. Naval air depots, like the one at Omura, the largest government-owned producer, so heavily damaged production was negligible thereafter. All the larger and many of the minor aircraft production centers, from one end of Japan to the other, came under the devastating attack. The Aichi plant at Nagoya and the Hitachi company at Chiba and Tachikawa destroyed. The Kawanishi plants at Himeji, Akashi, Naruo, and Takaratsuka destroyed. The huge propeller plants at Osaka, Shizuoka, and Amagasaki, a vital 5 months of production, destroyed. Following the initial B-29 strikes, a panic dispersal of the industry took place. By late spring of 1945, production tools and personnel had taken to the hills, causing further production stoppages. But by then, it was too late. Meanwhile, our strategic air attacks on another primary target had taken their toll. Japan's oil refineries and storage depots were high on our priority list. By May of 1945, overwater supplies were entirely cut off, and the precariously small remaining inventory of fuels and crude oil were under attack and running dry. The Ube coal liquefaction plant, one of Japan's largest producers of synthetic fuel, was 100% destroyed. In a single attack on the Oshima Naval Oil Storage Depot, 45 of its 50,000 square feet were destroyed. The Nippon Oil Refinery and Tank Farm at Amagasaki, destroyed. The Otaki Oil Refinery, destroyed. The synthetic oil plant at Tokuyama, destroyed. Every major oil source was wiped out. So desperate was Japan's oil situation that in 1945, pilot training was progressively reduced until it reached a level of less than half of the barest minimum number of hours needed to teach a man to fly. Remnants of the once powerful Japanese fleet were in port, immobilized, and later destroyed at their moorings. The period of air attacks on Japan proper saw Army and Navy ordnance plunge to disastrous levels. In less than a year, production in the arsenals of Japan was cut in half. The shortage of steel was so acute that Army chiefs in the field had been told that heavy artillery manufacture was being discontinued. An order had been issued